So in the last video, we talked about synthesizing functions from a set of harmonic frequency components. So the first part of the last lecture, we talked about Fourier synthesis. So if we take harmonic components like cos omega, cos 2 omega, cos 3 omega, or cos k, cos 2k, cos 3k, whatever you like. So you have multiple discrete harmonic frequencies at k, 2k, 3k, and so on. Then you can synthesize any periodic function using combinations of these discrete harmonic components. We saw this also on the computer animation that I showed you. So you just need to include a sufficient number of terms, and you need to weigh the amplitudes and the phases of these individual sine waves or cosine waves or e to the ikx's, whatever you call them or whatever you want to use, and then you can synthesize the periodic functions. We also saw that the inverse operation is to obtain the amplitudes of the individual frequency components. And so these are the coefficients ck that we looked at in the last lecture. And we saw that we do this by taking the periodic function whose frequency components we would like to find out about and performing an integral over one period, multiplying by e to the minus ikx over that period. And then we saw that the next stage of this is that you can take any function you like, and if it has a spatial representation in x, it will have a corresponding representation in Fourier space, in frequency space, with frequency components fx. And what we found is that the operation of taking a Fourier transform yields the spectrum, the continuous spectrum of frequencies and amplitudes of the function that you're interested in. And let me pick up from there now. And so I go back to the visualizer and just recap this. So we said if I have a function g of x, and I take an integral of this form, g of x e to the minus I 2 pi fx dx, then that returns the frequency spectrum g f of x. And x and f of x are a Fourier transform pair. Okay, so for example, x may have units of meters and f of x will have units of per meter. So these are spatial components. So you see they're inversely related with one another. And so this is called the Fourier transform. So this is called, that is equal to the Fourier transform of g of x. The inverse operation of this is if you have a spectrum of frequencies, g of fx, then you can work out what the real space function is, g of x, by taking the inverse Fourier transform. So it's an integral that looks almost identical. G of fx e to the I 2 pi f of x. Oh, there's an x missing. That's frequency, spatial frequency along x, and that's x, the real space coordinate, times x dx fx. So now we are integrating with respect to the frequency components, and so that becomes g of x. And so this is called the inverse Fourier transform of g of fx. I would like to pause here. So let's call this called the Fourier transform here. So this operation is the Fourier transform. And what it does, it returns the spectrum of the function g of x. So this is called also, you can call this the Fourier transform, or the spectral analysis if you want, because you get the spectral features back, and so on. And this here is called the inverse Fourier transform, this operation. And it is called the synthesis, because you take all the spectral components, you take the right phases, and you add them all up and integrate, and you can get the real space function. Synthesis. And one thing I would like to point out again is that actually these two operations look almost identical. The only difference is that there's a sign change. Actually, that sign change is, for our purposes, completely irrelevant, because it really is just a phase difference. If you take I or minus I, there's just a different phase that you get in there. But when we take intensities at the end and multiply, actually, it doesn't matter for the purposes of this course whether you have the minus there or not. You end up with something that looks that yields the same result. So in terms of, you know, a forward transform and a reverse transform, so we can call this a forward transform as well. So all these terminologies you will hear and you will use, and they make kind of sense, right? So you perform a forward transform to get this frequency content. You take an inverse transform to get the real space content, and of course, since we are dealing with intensities, actually the sign here doesn't really matter very much. So they are completely symmetric operations as far as optics is concerned. And now I will draw again our important 4F imaging system with all the conjugate planes. So we now have a sample plane. We call this back focal plane here. The back focal plane is also called more usefully the Fourier plane. And then here you've got the image plane. And so you can now see, going from here to here performs a Fourier transform. You get all the spectrum, so from the sample. So if, let's suppose I have a structure that looks like that, I will get the frequency content in the Fourier plane. So I will end up with this g of x here. And then in the next step, I take another Fourier transform going from here to there. And of course, the lens doesn't do signs, you know, minus I or plus I, but it doesn't matter. So it performs the same operation again, but now on the spectrum, right? And then it will yield something over here that mimics what the sample was, but of course not all the frequencies are accepted from the Fourier plane, and therefore you get image degradation. So let's just see this. So you have a spherical wave coming out here, parallel wave from this point, parallel wave, plane wave, sorry, and then you form back a, you get your image point over there. But it's now synthesized with a subset of frequency components. And like when I synthesized functions on the computer app that I showed you, if you don't take enough components in, not enough frequency components to synthesize your function degrades. And as a result of that, the image is degraded. We don't get a perfectly sharp point. We get a point that's essentially the Fourier transform of this, which is a Bessel function, or the point spread function. Okay. So let's now go back to Fourier transforms in 2D. So this is 1D, but if I go to 2D, we can write the same thing again. So if you have proper 2D apertures, we now have frequency components, not just along spatial frequencies along X, but also along Y. So have a look at my shirt here. Usefully, you can see this under the projector. Of course, you see I've got this checkered pattern. In fact, they are diagonal, these patterns, little diamonds if you so want. And so there will be one frequency component. One frequency component will be down in this direction. So every 2 millimeters or so, you get a new blue line. And then, of course, in this direction, I have another spatial frequency because, so again, every 2 millimeters, it changes. So all I need to do is I need to say, okay, in this direction, I have this frequency. In this direction, I have this frequency. With those two numbers, I can reproduce that checkered pattern. So from the frequency spectrum, I can get this real pattern in real space by just actually, for this simple pattern, by giving you two numbers. I need to know the amplitude in this direction and the frequency. I need the amplitude in this direction, the frequency, and add them up correctly. And then I have this pattern completely specified. So here in 2D, you perform an integral over both coordinates, and now your function, like this checkered pattern, is a function of x and y, and the Fourier transform is minus I times 2 pi f of x, x, plus f of y, y, so spatial frequency along the y direction, spatial frequency along the x direction, and we integrate over dx to y. Otherwise, there's no difference. And then the Fourier integral. So this is also the inverse Fourier transform is then given by g of x, y. It's taking the spectrum and summing up all the phases and amplitudes of the individual spectral components. Dfx, dfy. And again, the signs here are not important. Okay? So that is in effect what we're doing. So all we need to know is, if we have certain patterns here that I want to image, these patterns, we take the Fourier transform, and then we take another Fourier transform, and then we get the image from that in real space. So let's look at some properties of the Fourier transform. So Fourier tricks, I call this, in the lecture notes. So if I have a function g of k, it's the Fourier transform of g of x e to the minus I 2 pi fx times x dx. Then I can also write this function as g of fx. So we call this g of fx is equal to, you can write this as a complex number. I'm making a bit of a mess here. G of fx times e to the I phi of fx, right? So where this is called the amplitude spectrum, and this is called the phase spectrum. And so you saw exactly on the app what this means. So you could have components e to the I 2 pi fx times x, and you multiply that over the entire frequency spectrum, so you get the amplitudes, but then you add them at the right phases as well. Each one has to have the right phase assigned to it, and then you can, with that, make any function you want. So this is just another way. So in general, the frequency spectrum will be a complex function, and so the complex function can be written as amplitude and phase as any complex number, and so that will make some things easier to understand depending on the problem. We will think of it in terms of discrete frequencies in real space, sort of discrete components, real components, or we will think of it as in terms of phases and amplitudes. So this will become clear in the examples that we give. Right. So now we need to look at some important tricks. We are not interested in doing heavy maths. It's worth doing a few exercises so you get the hang of it, how to go from one representation to the other, from space to frequency space. So you'll do a few examples in the example sheets. But then actually we're not interested in doing heavy maths here. We are interested in using the results. So we will often give the results of some of these Fourier transforms. They're known, you know, there's nothing interesting about them. You do them once and then you just use the results. Once you notice, you know that a rectangle function gives you a sinc function, a circular function gives you a circular top hat gives you a Bessel function, and so on. And there are lots like that that you'll just use. They'll be given to you, or if in simple cases you might be asked to work them out. But then always on the understanding that we only do the simple functions. And so the most important first function that I would like to discuss with you is the delta function. The delta function. The Dirac delta function, as it's called. And it is defined as following. The delta function is defined as delta of x. It is equal to 0 when x is not equal to 0. It is equal to infinity at x equals 0. And another definition, and another property of it is that the integral of from minus infinity to the infinity of delta x dx is equal to 1. So it's an infinitely thin but infinitely long function centered at 0, the delta x, which has an area that is equal to 1. So one draws this function. It's of course one hard to draw because you can't really see it, but one would draw this function like this, and one makes an arrow because of course the value at 0 is not 1, it is infinite. But what this is supposed to mean is that actually what I'm representing here is the area of that function. And so I draw it with an arrow. So that's the delta function for this representation. And then you can get a displaced delta function. So, or shifted delta function. So the shifted delta function, if you shift it by an amount x naught, delta of x minus x naught is equal to naught when x is not equal to x naught and is equal to infinity when x equals x naught. So what this means is that this function looks like this. So a shifted delta function, so that's 1, and so that's x naught and x, and so that's delta of x minus x naught, shifted by an amount x naught. Okay, and so there's an interesting property now with this. Because the integral of this function, the area of this is 1, this turns out to have a useful property for us. So, for example, and the property is called the picking property. Because if I have a function, let's suppose I have a function g of x, and I have this delta function here, and if I now integrate delta of x minus x naught times g of x between minus infinity to infinity dx. Now what happens? So of course this product here will be 0 anywhere outside of x naught, but when you hit x naught, then of course the integral will be 1 times whatever the value is at that point. And so what you end up with is just the value of the function at x naught. Okay? And so this is quite interesting, because what this means by defining this Dirac delta function in that way, shifting it, I can actually make it sample, any function, and get the magnitude of the function at that point. Now, one way, how could we make a delta function that has these properties? How could we define it? And one way, and the way we will define it, is if I go back to using k for the frequencies. So you remember fx is equal to 2 pi over k, the way we've defined it. But if I define the delta function as follows, is equal to minus infinity to infinity e to the I kx dk. This turns out to have precisely the property that that gives you an area of 1 when you integrate from minus infinity to infinity, right? And at x equals 0. So it has exactly this kind of property. And so what this looks like, in fact, is very similar to what the Fourier transform looks like. Let's have a look. We go back to our original function. Let me just have a look if I find it. I can show this in the lecture notes. So if you compare this function here with this function, then what this looks like, so you remember this here is just k, so this is equal to I kx. So this would look like synthesizing a function with one frequency component centered at 1. Let me just repeat this and be clearer about this. So if you look at this definition of the delta function, it looks like the sum of an infinite number of frequencies, all with amplitude 1, right? So it's 1 times all these frequencies over all frequencies. So in fact, this delta function contains any frequency k that exists. It's a continuous spectrum of all frequencies from -infinity to infinity. And you add them all up, and when you add them all up, actually what you end up with is just one single peak that's centered around 0. So comparing it to this original Fourier synthesis integral here, so what this means is that this spectrum here is just 1 for all frequencies f of x or k, whatever you call it, and you sum them all up. You can kind of see why that happens. If you go and play with the app, the Fourier synthesis app, you can see what happens to get this functions from harmonic components. You meet all frequencies. So let's start with a frequency like that. And then let's take a faster frequency. Let's take one frequency that looks like this. And then take another frequency that's even going quicker than that. And what you can see is that if you do this for all frequency and make sure that the phase is centered at 0 for all these frequencies, then you get this peak here rising at around 0, and very quickly as you go away from 0, there will be lots of components that come out of phase, and when you add them up, they add up to 0. These frequencies, because the phases will be randomly coming out of phase. So the more frequencies you use, the higher you push that peak in the middle, where everything is in phase, even if they have different frequencies, right? Because all of them have the same initial phase. And then once you, and so if you put them all with the same amplitude 1, put all these components in, then you end up with the delta function. And that's what this means. So in other words, the delta function contains an infinite number of frequencies. It contains all frequencies. To synthesize a point, you need an infinite number of frequencies. And so in the microscope, of course, a point source, a point emitter, it has an infinite number it requires an infinite number of spatial frequencies to synthesize, which you can't pass through the microscope, and therefore you get image degradation. Okay, so I can do now the same idea. If I want, you can also see what happens. If I want to shift that delta function to a different position, if I want to shift this delta function out to x0, then what do I need to do is I need to shift all these frequencies so that they all lie in phase at the correct point, and come out of phase away from that. So you have to shift it by this amount. So in other words, just to make sure, the spectrum of the delta function is the Fourier transform of the delta function, and it is just 1. So it means that the amplitude of all frequency components is 1 for any frequency. And in other words, you need an infinite number of frequencies to synthesize the delta function. And the displaced delta function, delta of x minus x0, that has the same amplitude spectrum, g of k equals 1. But the phases are all shifted. They are shifted. The phase spectrum phi of k is such that f of delta x minus x naught equals e to the minus I k naught. Sorry, I'll do that again. Is equal to e to the minus I k x naught. So each component at frequency k will have to be shifted by x naught, k times x naught. Okay? I leave that as an exercise for you to work out. And you can try this by seeing, if I take, let's take some discrete frequency. You can just try this by saying, let's take one cosine wave, which has a frequency k, and then take another one at 2k, and then at 3k, and now shift the phases for each one by exactly enough so that the phases overlap correctly at x equals x naught. And you will see that you will have to produce a shift like this that we've just shown you here. Okay, so you'll get plenty of exercises in the supervisions and also by practicing on the example sheets on Fourier transforms. And so I will just go through a few here as examples. So let's then start with some standard Fourier transforms, because actually we won't need all that many for this course, but it's nice to have a few in the bag, so to speak. So if I have, let's suppose I have a real space function f of x, and it is 1. It's just evenly, it's just an even, for example, an even illuminated object. The object is just even everywhere. So all across x, you just have one value for it. The value is a. Then the Fourier transform operation for this, well, what does that yield? So this means take, so this means that the frequency spectrum here just has one component. So so if I have the frequencies here, this yields the delta function, just as we saw earlier on. So I could go from this way to that way. I could say the frequencies of a delta function contain an infinite number of frequencies, but the other way around, I could just say, well, if everything is even, then essentially I only have one frequency in this spectrum here, namely a DC component at frequency 0. Okay, so this is just an even illumination. Then let's take the next example. Let's take this example. Let's have a function like that. So this is a cosine function, a cosine of k naught x, and so this is x, and then the frequency of that will be, you will get one component at plus k naught and one component at minus k naught. And why is that? So if you think about this, you will have frequencies e to the I k naught x plus e to the minus I k naught x. And so if you think of this is a real function, right? So the cosine function. So if I take these two complex numbers together, e to the I k naught x and e to the minus I k naught x, then I end up with a cosine k naught x. In fact, I end up with 2 times a cosine k naught x. So what I need to do is I need to reduce the amplitude of these. So if this is amplitude A, I need to make these amplitudes A over 2. And you can work that out yourselves by just taking the Fourier transform of this simple function. So what you would do is you take the integral between minus infinity and infinity, a cosine k naught x, and then you integrate, you multiply by e to the minus I kx, and you integrate with respect to dx, and you should end up with exactly this, these two components, right? Now, if you make this spacing larger, so if the frequency is slower, then in fact these two become narrower, right? Because they are inversely related. So you see some examples here. You see, for example, this is a slow sine wave. So here the two frequency components are close together. This is a faster sine wave, and here the frequency components are further apart because the frequencies are higher in here. This is a sine wave, a cosine wave that has a DC offset. So it will have the frequency components of the cosine wave, but also a DC component here. So if it's shifted by A, there will be a DC component, A shifted, because it's essentially that function plus that function. So you get this function plus that function also in Fourier space. Okay? You can think of it again in terms of complex numbers. So if I have a function, a sine function, for example, a sine k naught, that's exactly the same as a cosine function, except it's shifted in phase, right? And one way to achieve that phase shift is just to make one of these frequency components negative. So you have e to the minus k naught x plus e to the plus k naught x, like that, right? And then you know, by flipping those over, that leaves only the sine term in your function. That is the same thing as using the original and multiplying this function with a phase factor. So here you see that. I could say, let's just take the magnitude of the frequency spectrum here. The magnitude is exactly the same as it was for the cosine, whether it's sine or cosine, doesn't matter, it's just the frequencies. So just the frequencies, but then you add the right phases for these frequencies. So you add a positive phase for that one, and you add a negative phase for that one. That shifts the function accordingly, right? So both of these ways of thinking are work that way. And so here are some important Fourier transforms that crop up all the time. The rectangle we've already done. We've worked it out for the slit first, then we've worked it out with the Fourier transform, and we saw that the rectangle function has a sinc function as its transform. Sinc obviously gives you a rectangle, the other way around, right? So the comb function gives you another comb. We will practice some of these as well. So, for example, if I have a, let me see, if I have a comb function, let's have a look. So let's make a comb, and this is x. Then if I have a series of delta functions spaced like that, and these are all spaced by a, then the Fourier transform of that is again a comb, but here the spacing is now 1 over a. Something like that. Okay? You will practice these yourselves, but you can see, again, so if you have a narrow function, comb function like this, then the frequencies in the Fourier transform, as you go from here to there, then if they're narrow here, they will spread out in Fourier space. So the frequencies will spread out. So narrow frequencies in real space, wide spatial frequencies in Fourier space, right? So if this pattern, so for this fine pattern here, you get a relatively wide spacing in Fourier space. But if the checkered pattern is much larger, then of course in Fourier space the pattern will contract because the frequencies are lower. Okay, so other important ones are a Gaussian. If you have a Gaussian function that looks something like this, so something like that, then actually a Gaussian, its Fourier transform is again a Gaussian. That's quite an interesting result, right? So you won't be asked to derive any of these. You will be given them, but you will get practice. So it's really just worth knowing a few, like a sinc, a rectangle. Other interesting ones are the square, the rectangle we've done, are of course the circle, which is a Bessel function, right? So here you see that if you have a circular top hat, you get a Bessel function in Fourier space. Okay, so the final bit I want to do with you today is the convolution theorem, because that's the final piece we need, and then we have all the math. The convolution theorem. Then we have all the math we need to do imaging. If you have two functions, f of x and h of x, then the convolution of these two functions is g of big X is equal to f of x h of x minus x dx. So we integral between minus infinity and infinity. And so this looks like a horrible function, but essentially what you have is, if you take a variable x and you shift essentially what you do is you take your original function f of x and you multiply it by the original function h of x, but now with x taken negative, h of minus x, so you flip the function and you shift it by an amount of x. So you take two functions like this, you take two functions like that, g of x and h of x, you flip h of x, and you perform the integral by sliding this function across the other, and so you're taking the product at each point and summing up the different pieces, summing up the overlap. And you think, okay, well, what do I need this for? In fact, the imaging operation in a microscope is a convolution operation. You will see that in the coming lecture. So the convolution theorem states that if you have the Fourier transform of the resulting function, the convolution function, is equal to the Fourier transform, of course, of the convolution. We write the convolution often as we write the convolution often as f of x, and then this is the convolution operator times h of x. So it's f convolved with h. And the convolution theorem states that the Fourier transform of the convolution of two functions is equal to the Fourier transform of f times the Fourier transform of h. So in other words, the convolution theorem states that if you want to work out the Fourier transform of f convolved with h, that's the same thing as taking the individual Fourier transforms of f and h and just multiplying them. And so I would like to show you one quick example of a convolution operation. And we'll just do this pictorially, and then work out what and give you an idea. You will practice this also again in the using the sheets, the problem sheets. But we'll do one quick example together, and then we go to Young's slits via the convolution theorem.